Hello, everyone. A couple of administrative items before we get started. Due to the large number of attendees, we will be muting everybody's microphone during the session. You can type questions in the questions pane located in the control panel. I'll answer some questions at the end of the session. Also, feel free to send us comments about the webinar or additional questions at webinars@csiamerica.com. Also, all webinars will be recorded and posted on our website after the session. Okay. So in this example, I'll define a time history function and show you how to apply it to the structure. I'll define a time history load case, going through each one of the parameters in depth. Then we'll take a look at some output, including plot functions, response spectrum curves, and I'll show you how to generate a multi-step animation AVI. Lastly, I'll pull up a model and show you how to define and apply blast loading to a structure. Okay, so today's session is on time history. Time history analysis is a step-by-step analysis of a dynamic response of a structure to a specified loading that may vary with time. So there are three different ways to actually apply time histories in ETABS. First, you could define a function and apply it as a load pattern, for instance, as a wind load. Second way is to perhaps apply as a walking vibration. So if you go underneath the define menu, clicking on walking vibrations, this allows for automated application of vertical pulse loads across a floor to dynamically simulate the footfall of a person walking. Now, we won't be discussing this in today's session, but we do have a detailed watch and learn that can be found on our website. Lastly, and this is the item that we'll be discussing here today, is defining a ground acceleration and applying that to the structure. All right, so let's get started. So the example you see on the screen, it consists of three simple 2D frames, which will be subjected to a modal time history analysis with the use of link elements. So the frame on the left here has no link properties assigned to it. The second frame contains damper link properties as its lateral force resisting system. And the third contains isolator elements. Now, I want to reiterate that we're not going to be discussing the nonlinear properties of these link elements in detail, but rather concentrate on the time history portion of the model. Okay, so why don't we go ahead and define a time history function. This can be found underneath the define menu, functions, and you can see time history is available. We do have many functions to choose from, including sine, cosine, sawtooth, and triangular. If I just open up one of these, you can define the time versus acceleration values manually here in this form. But for today's session, I was going to use a function that's been embedded in ETABS from our time history functions, many to choose from. So that can be underneath the From File tool. And we'll click Add New Function. So what I'm going to do is under the function file, I'm going to browse and look for the digitized file. And this can be found in the folder where ETABS has been installed under Computers and Structures, ETABS 18, and you'll notice there is a time history functions folder. So for today's session, we'll be using the El Centro digitized file. So this is how it comes in. Let's take a look at the file first before we make any changes to the parameters. So if we click View File, you can see a digitized format pops up. These are time and acceleration values. You'll notice that there are 3 time acceleration values per line. Now that's important to note because if I go back and click on number of points per line, I need to hit 3 to ensure that ETABS recognizes all the points and brings them into the program. Now, header lines to skip. Now, these are all functions of the actual file itself. In this case, I'm going to skip 2 lines from the top. And these are time and function values. The other option is to select values at equal intervals, but that is not the case in this digitized file. Now, another useful tool is to perhaps converting this to a user-defined file. If I click on this, you can see all of the values have been taken from that digitized file and imported directly into ETABS. Now, this can be very useful for when you're sending a file to somebody else. You do not need to include that digitized time history function file anymore. It has been automatically imported directly into the program. Okay. So now that we have the time history function defined as El Centro, we'll click OK here. And now we'll go and define the time history load case. I have one predefined, and we can take a look at this. Modify show. So for this specific model, we're going to be using a linear modal analysis. But let me just show you the different options which are available. Nonlinear modal, linear, and nonlinear direct integration. I'm just going to select one of these just to discuss some of the options. So for initial, let's click on, FNA. So for initial conditions, if I were to use this nonlinear modal FNA option, there are 2 different initial conditions to choose from. So if I selected 0 initial conditions, this essentially means the structure has 0 displacement and velocity, and all elements are unstressed. And we can also select the second option, continue from state at the end of an existing nonlinear case. This essentially means the displacements, velocities, loads, and nonlinear deformation histories from the end of a previous analysis are included prior to applying the time history acceleration to the structure. So those are the 2 different initial conditions options if you're using nonlinear time history analysis. But for today's model, we'll be sticking to linear modal. Actually, for the second model I discussed for blast loading, we will select nonlinear modal FNA. Okay. Now for the loads applied, there are 2 different options. You can choose whether the load is to be applied as a load pattern or built-in acceleration load. So we had just defined that El Centro time history, so we are going to apply that as an acceleration in the X direction, which is the U1 direction. Program has built-in acceleration loads, U1, U2, U3, as well as R1, R2, and R3. All the U's correspond to unit translational acceleration to the ground in the X, Y, and Z direction respectively. And the Rx, Ry, and Rz correspond to unit rotational acceleration about the X, Y, and Z axis. So we'll select the El Centro function, which we've just defined, as well as the scale factor. Now, scale factor is a common question. For acceleration loads, the scale factor has units of acceleration. In this case, we are in inches squared per second. So we're going to be using the G factor, which has been converted into 386, which is essentially 32.2 multiplied by 12. I think it's 386.4 actually. Okay, so for other parameters, this is a linear modal time history. Time history motion type, there are two different options, transient. Now, this is the most usual case where the structure starts at rest and is subjected to specified loads only during the time period that we specify. So I'm just going to bring up this digitized format file for 1 second again. Now I'm interested in taking a look at the length of the file. So you'll see here it's around 12 seconds. You can see that the last data point is 12.11 seconds and the acceleration is located or is 0.086. So that's important to note the length of the record, because when we define the output time, a number of output time steps, the product of the time steps multiplied by the time step size should equal at least the length of the digitized record, which is 12 seconds. So a couple of notes about this. The output's time step size is the time in seconds between each of the equally spaced output time steps. Now, it's important to note, do not confuse this with the time step size in your input time history file. The number of the output time step size can be different from the input time step size. And let me clarify what I'm talking about. So let's click OK here. If we go quickly back to the functions time history. Now, this is the value. Remember, we did not select equal intervals of 0.02 because that is not how the digitized format was generated. So it read the files directly, time versus function, which is acceleration in this instance. So we go back to the time history load case. It's important to note that this value can be different and typically is. So I've selected 600 output time steps times 0.02, which is 12 seconds. Okay, and lastly, for the load case data, we can take a look at modal damping. I have a little analysis reference. This is taken from our analysis reference manual. It describes the modal damping in great detail. So it has two different sources, which are described as the following. It's important to note that damping from a program automatically makes sure that the total is less than 1 based upon this equation for damping here. Now, in this example, I'm going to be using a constant damping for all modes, but you do have two other options. Interpolated damping by period or frequency, as well as mass and stiffness proportional damping by coefficient. We're going to keep things simple in this example and keep the constant damping set to 0.05 for all modes. Okay, so we have defined the time history function. We've defined the time history load case. Let's go ahead and run the analysis, because there's lots of output that can be viewed directly about time histories. So if we click the Run Analysis button here, this will just take a second to run. Okay, Okay, so underneath the display menu, we can take a look at, first of all, some moment diagrams. And we can select the L case 1 as the time history load case. And we can select on take a look at the moment diagram at a specified time, max and min, or max or min. So we can take a look at this. So you see here, you'll notice that the moment diagrams for the first two frames are very similar due to the fact that the dampers did not take any nonlinear action. But you'll see the isolator has a much different moment diagrams as the first two. So if I take a look at this as a function of time, I'll click apply. Now this is starting at the zero stress state. Now what we can do is step by step, you can see that at every time increment of 0.02, you can see how the moment diagrams are changing accordingly. And you could step through the whole 12-second digitized format by clicking on the arrow buttons here on the bottom right-hand portion of the screen. We don't need to do that. What I'll do here at the end is create a AVI file going through the whole 12-second time history. We can also take a look at deflected shape for the absolute max as well as absolute min. Now if we take a look at the deflections for the first two frame elements, you can see it's in the order of maybe 3.5 inches for the first two and about 5.2 for the third frame located on the right hand side. Now there are many different ways to view output here in ETABS. This is the more typical way. Now let's take a look at some plot functions, which essentially we can take a look at displacements over time. We can take a look at how the forces changes over time in a nice graphical output. So to view that, we can take a look at display, plot functions. Now there are many different things to view here. What we're looking at now, and this is kind of the default, is the base reaction over time. And this is for the entire structure. So before we do this, let me just go back here. Now I'm interested in getting information about 3 separate points. Let's select them. So we'll select these 3 different points. And what we can do is take a look at deflection over time for all 3 of these joints simultaneously. So we can see how each one of these 3 different frames react based upon the time history that was applied to it. So once we have those selected, let's just go back to plot functions. And we can define the plot functions. So here are those the joints that I'd selected, joint 2, 4, and 6. And what I've selected here is a joint displacement, but there are many different options to choose from. I could click on joint velocity, joint reaction, accelerations. There's column forces, which we can take a look at. So there are many different options to choose from when you're taking a look at output. So this is on story 3, joint level 2, and we'll look at the displacement in the X direction. And I did this for joints 2, 4, and 6. Now, to view them on the screen, I'll need to select these joints, move them over to the selected functions, and I'll remove this base function fx. Okay, so there you have it. You'll notice that joints 2 and 4 have very similar deflections. Actually, they're identical. And the deflection of joint 6, because it had the isolators, you can see the deflection is much greater. And you can see how joints 2 and 4, the deflection kind of dissipates over time as we reach the end of the record. So this is very useful information. You could do this for as many joints as you like simultaneously. We can also take a look at reports that can be generated if you click on the Show Report button. Summary report, detailed reports, these can all be saved into a nice format as well. You can see not only graphically, you can see them on the screen, but the tabulated values are shown here as well. Exporting to an Excel format. So there are many different tools available to the user to export and view the information. Okay, what other output can we take a look at? Just going to close these out here. Oh. That's all right. We'll just open this file real quickly. Okay, so we looked at plot functions. Let's take a look at story response plots. So under the display menu, we can take a look at story response plots. Now under the display type, we can, right now what it's showing is maximum story drifts. We can also take a look at story shears. In this case, in the global X direction, we have a story shear. We can take a look at overturning moments as well as story stiffness. So there are many different outputs that can be viewed. Now let's take a look at L case once. So now we're looking at this over time, how the story shears are changing. We can take a look at global X as well as global Y. Lots of information to be viewed in reference to time history. So we can also take a look at response spectrum curves. So you can have response spectrum curves calculates the curve at any specified point. So in this case, I'm looking at joint label 1, and it's calculating for many different damping ratios. So I can set these down here at this portion of the screen. Right now it's selecting all the damping ratios at once, and I have the ability to select between many different joints, and you can see how the response spectrum curves are changing accordingly. Also under the display menu, we could take a look at, that's all right. So what we can do here is we can animate this, and the input function is being shown, and I'll just increase the animation speed. And you can see over time, what this is showing you is animated plots showing story acceleration, drifts, shears, all on the same plot. So this is kind of a useful tool to take a look at. In this case, displacement, absolute acceleration can be viewed in the different directions, as well as this is the load step that's being shown simultaneously for this time history function. And under this cumulative energy components, showing you step-by-step energy plots and tabulated results for time history load cases. So you can see it's showing the kinetic energy, potential energy, and this specific model, a lot of this has been due to the global damping. You can see the entire record is being shown from 0 to 12 seconds and how the energy changes during that span. So a lot of information to be viewed in reference to time history analysis here in ETABS. I promised to show you guys how to create an AVI video as well. So after you run the analysis, we can take a look under the File menu and create video. And multi-step animation is what we're interested in. You need to give this file a name. And so we can select the load case, the start and end time. In this case, it's going to be the full length of the digitized record. Time increment. Now, for example, what this time increment means is a picture or frame of the deformed shape is created for every 1/10 of a second of the time history. So in this case, every 0.1 seconds, something an image will be recorded. And then we have options for cubic curve, absolute displacements, and magnification factors. I went ahead, it takes a couple minutes to generate, but I went ahead and created this. And let's take a look at this. Which one is this? Let's take a look at this one. We'll open this. Okay, maybe it's this one. Okay, so of course you can see the magnification has been exaggerated drastically. I think it's like 50 times. So what I did in this one is, I'll just run that one again. So you can see here how the moments were changing over time, and I included the deflection in this video as well. So to create that, you just need to make sure that the moment diagrams are being shown prior to creating that video. So if I just click the undeformed shape, we'll turn off the extrusion here. And we'll click on the moments to be applied. So as long as this is showing on the screen, and then you go to File, Create Video, that is how you get the moment diagrams included in the video as well. Okay. I'm just going to bring up a simple template model to talk about blast analysis here. And we'll just open this up, called blast. So very similar to what we just did. The main difference in blast analysis, and I'll just turn on the extruded shape, and what we need to do here is something different compared to the first model. In the first model, we defined an acceleration and applied it to the structure. What we're going to do here is apply a load in a load pattern and then generate a blast function. I'll show you how to do that. So first of all, I'm going to select this joint here. This is the point where the blast load is going to be applied. So what we need to do here is first assign a joint load, which I've already done, but let me just go through the steps. So if we go to assign, well, let's unlock the model first. We'll click on assign, joint loads, and then force. I've created a blast load pattern, and we'll just select maybe 30 kips, and we'll replace the existing load. We'll click apply. Okay, so you can see this 30 kip load has been applied in the X direction. Now, if we go to define functions, time history, instead of using a digitized record that was pulled from the time history functions folder, we're going to create our own function. And it's going to be a blast function. If I just modify show this, so it's kind of like a pulse load. We're going to start from 0, apply the load very quickly within a second, and then the load will be taken off very quickly. So this can be even quicker than this. I created one for 2 seconds. It could be 1 second. It could be half a second, whatever you want to do. But the point is that this pulse loading was added very quickly from a 0 state, applied at 1 second, and then taken off very quickly. So that's the major difference between the function that we generated in the first model compared to this one. So we'll take this function, it's called blast, click OK, and following the same pattern, we'll go to define load cases, and we'll click on modify show. Now, the main couple differences here compared to the first model. As I'd mentioned, we're going to run a nonlinear modal FNA, time history analysis. And secondly, instead of applying the load type as an acceleration, we're going to apply it as a load pattern. we're selecting that blast load pattern that we defined and leave the scale factor as 1. Leaving the scale factor as 1 is because I've already defined the magnitude of the load in the blast load pattern. And we'll leave all the other items as default here. Let's go ahead and run the analysis, and we'll take a look at some similar output, including the plot functions, displacements, how the column forces change. Let's just quickly run this. Okay, so we're going to select that joint, and we'll go to display, back to plot functions. So this is what it's showing me now. This is just the base reaction as a function of time. You can see the load is applied at 1 second, and you can see how it dissipates over, and I ran this for 10 full seconds, so you can see how the model reacts after it's subjected to that load. But what I want to look at is take a look at displacement for that specific node. So we can click on FX. This is that F1 joint that I defined, and we'll click on joint displacement. That's what we're interested in the X direction. So we'll do the same thing. We'll swap these out, moving the base function on the left. And here you go. For this specific joint, it's showing me deflection and how that specific joint changes over time. So we've looked at deflection. We can also take a look at column forces. So if I go back here and select the entire column and go back to plot functions, I'll add a new, let's see. Okay, I'm going to make sure that's selected first. Okay, so column force, and there's that PF2 function name. And so what we need to do is, just as we've done before, we'll enter PF2 in here for the function itself, and there you have it. You can see for the column forces how the column force changes over time, and then you can see how the load is applied, taken off, and how the force changes over time. Okay. Okay, so let's take a look at some questions here. Okay, excuse me. Okay, there's a question about what scale factor should be used. I touched upon this before briefly, but when you're using a load pattern, if I just bring this up, so say we're using a load pattern. When the load type is set to load pattern, the values of the time history function are multiplied by the scale factor to produce unitless terms. So remember, I left the scale factor as 1 because I'd already defined that blast load analysis. Blast load is 30 kips. But if I'd left that, if I defined the blast load as 1 kip, I could set the scale factor here to 30, and you'd get the same result. So that's how it's done for load patterns. But for acceleration, it's a little different. It's a function of gravity. So you'll need to set the scale factor based on the units. So I was using inches squared per second That's why I put in that 386.4 value. If I was using feet squared per second, it would be 32.2. So it's a function of g. How are time history results displayed at each time step? So if we take a look under the display menu for show tables, for joint output, we can take a look at displacements. And if I click modify show, you can see here modal history results. I can click on, it can show information for envelopes. It can show information as a step-by-step. So you need to make sure you click step-by-step if you want to get information for each specific step in the output tables. I click OK here and click blast, make sure that load case has been selected. And all of these tables have been showing up now. So for joint displacements, we can take a look at time history, and you can see each step, 5, 5, 3, 5, 4, 5, 5, information for each step is now being shown. So the question about how to perform time history analysis for wind load. Now that's using the same tools as I did for the seismic analysis. It was pretty, for the blast analysis. Let's bring up that one. So I had just defined a single point. You could define many different load patterns with many different loads, and include those many different load patterns in the load case. So for example, let's bring up this blast. I just selected one load pattern. You could have 30 in here with all different wind loads applied to them. So each wind load pattern can have a different load associated with it, a different scale factor. So this was a very simple case, but you also could include wind load in this load case data form. Another question, can we do time history analysis in two directions in one analysis? You can, yes. You need to be careful as to viewing the output because it can get a little muddled. I prefer to do them separately, so you can kind of take a look at the output individually. But yes, you can do a time history analysis for accelerations in different directions in the same load load case. Okay. Again, I wanted to thank everyone for joining us today. I'm going to bring up this, if you have any comments or questions, again, please feel free to contact us at webinars@csiamerica.com. You'll also be getting a survey after the session has been concluded. And feel free to make comments and have questions included in that as well. We'll post this video sometime this week, as well as answers to all the questions that not only were asked in the session, but also that are questions that we didn't get to today and questions that were emailed to us. So those answers will be posted on our website as well. So thank you very much for joining me today, and please take a look at our website for further webinars. We have one on Thursday, Response Spectrum, that's July 18th. And please check our website for future webinars. Thank you very much.